All right, so I'm now recording the session. We'll get started here on some different things. So with this, first of all, I do want to put up some abbreviations. You should write these down. The first is, okay, I see that Kylie's back, so we'll let her get logged in. But just write these in your notes so you can look at them. Upside down A, these are abbreviations that we're going to use. This means for all or for every. So like for all numbers, for all whole numbers less than 10, that'd be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So an upside down A means for all. A backwards capital E means there exists or there is. So there exists. So there, you know, we could use this. There exists an even prime number, namely 2. We could also say, you know, all kinds of stuff like there exists an odd prime number, even though there's a whole bunch, infinitely many of them. And then we have kind of a backwards curvy E means such that. Okay, and you're going to see why I'm using these abbreviations, because I don't want to write out like we had to all the time. So it's kind of like a backward elongated C. It's like a backward curvy E, letter E. That means such that. An arrow means implies, or if then, if A then B, or A implies B. So I'm just going to say implies. Basically, the conclusion would follow the hypothesis. And I think that, oh, and then I'm going to use, instead of saying some open interval containing A, I'm going to use I for some open interval containing X equals A. Okay, so I had this all written up, and then it erased it on me. All right, so these are abbreviations that we're going to use just to save us, save time writing stuff out. I'm okay to use them as long as you use them correctly, and I do expect that you know them. So there is going to be some memorization stuff with the formal definition of a limit. So let's go back to that definition. So definition. First thing we got to do is we got to make sure that F is defined. So let F be defined on some open interval I containing X equals A, or I got the hard to write. Son of a gun. I just lost it. So when I'm trying to write on the screen, it just, like if my hand hits something, it goes away. Hopefully you're all still there. It looks like you're still there. Let F be defined on I or I minus A. So some open interval containing A except possibly A itself. So that's X equals A. That's the X value that we approach from both sides. Remember, the limit of a function is the height it approaches as X approaches A. So then we can say, then the limit as X approaches A of f of X exists and equals L if and only if, so IFF is if and only if. I should have put that on the other, we talked about that yesterday. If and only if what? If for any epsilon greater than 0, remember epsilon is a tiny number, designed to be a tiny number. For all epsilons greater than 0, there exists a delta greater than 0 such that. So that's how I wrote that out in words yesterday, but this is a lot quicker to do it. So I'm going to read this second sentence again. So far I've got, then the limit as X approaches A of f of X exists and equals L if and only if for all epsilons greater than 0, there exists a delta greater than 0 such that 0 is less than the absolute value of X minus A is less than delta, would imply or guarantee that the absolute value of f of X minus L is less than that epsilon. So here's the formal definition. So this is a formal definition of limit of a function. Okay, so we're going to use this and we're going to actually prove these. You're going to have to do it on a quiz and a test with a line. Okay, now what this does is, if you remember, this gives this is a delta window around A. So it's a delta window around x equals A. And what this is over here, this is an epsilon window around the height of L. Remember, L is a height. It's the height that you approach. Now, I don't say here, the left one I said x equals A, but I did not say that f of x equals L because we don't know that we're actually defined at that height. Okay, so anyway, but that's the height you approach. So drawing a picture of this again, I'm going to draw a picture of it. Whoops, I got to go back. Share the whiteboard. I erased it. Okay, now I got it right. So drawing a picture of this, once again, if I have some function, whether I'm defined at that point or not, so that could be an open hole here. Here's x equals A. Here's the height that we approach as x approaches A from both sides. So once again, I'm going to use red from the right today. Try and use red from the right. As x gets closer and closer and closer to A from the right, what I'm seeing here is that my height would get closer and closer and closer to L from the right. So that's what we're going to call the right-handed limit. The left-handed limit, I'm going to use lime green for left-handed limit. As x approaches A from the left, we can see our function is going up and approaching that height of L from below. So anyway, if the right-handed and left-handed limits both exist and equal L, then that's actually going to be the limit of the function. And then the definition that I just gave you is actually a formal definition that we can actually prove for specific functions. We're going to do it for a line. So what I want to do, and then section 1.4, I think is very hard to read personally. It doesn't make any sense to me. So if it made to you when you read it last night, great. You're one step ahead of me. But I'm going to draw, or I'm going to give you a specific example where we're using this. And I'm going to use one that we didn't do before. We just let epsilon equal delta yesterday. We did one simple example. So today we're going to let f of x equal 4x minus 5. And we're going to let epsilon equal 0.01. So epsilon is going to be a tiny number. And we need to find a delta greater than 0 such that what happens? Where, or I could put that backwards, such that 0 is less than the absolute timeout. I want to let A, so f of x equals 4x minus 5, and I want to approach x equals 2. Let A equal 2. If you plug 2 in, this is defined everywhere. What height do you get when x equals 2? You're going to get 8, right? You're going to get 3, because 8 minus 5. So L is going to be 3 here. So we're going to prove this one today as well in general for any A and for any A here. But in this case, we're just going to do it in section 1.4. So section 1.4 does it for specific epsilons. Okay. So here in this case, if 0 is less than the absolute value of x minus A, so A is 2, is less than delta, which we need to find, that's going to imply that the absolute value of f of x minus L, so f of x is 4x minus 5, and then minus L would be minus 3, because that's the height I approach. So as x approaches 2, then this f of x approaches a height of 3. So f of x minus L here is less than epsilon. Of course, epsilon is 0.01 in this case. So what I need to do is I need to find this delta. So we essentially have to use the conclusion to come up with the hypothesis. So here's the conclusion over here. We need to use that to come up with the hypothesis and actually find that delta. So what I'm going to do on the right is I'm going to say, well, what's that imply? That implies the absolute value of 4x. If I simplify, absolute value of 4x minus 8 is less than 0.01. And everybody agree with that? So over here, really, I'm focused on the right side of this chain link or three-part inequality. I want the absolute value of x minus 2 to be less than delta. Well, I don't have the absolute value of x minus 2 here, but I could if I factor out a 4. So I'm going to keep going here. If I factor out a 4 in there, I've got the absolute value of 4 times the quantity x minus 2 is less than 0.01, correct? So now what I can do is remember my algebra rule that says the absolute value of A times B is actually equal to the absolute value of A times the absolute value of B, right? Absolute value meaning the positive part if it's a number, right? Anyway, so I can use my algebra rule there. Well, if I do that, I'm going to come back. I'm going to start over, or not start over, but do a new screen. So if I do that, I could say that that implies that the absolute value of 4 times the absolute value of x minus 2 is going to be less than 0.01. And of course, did you notice that I did not write it as the absolute value of 4? I just wrote it as a 4 because we all know that the absolute value of 4 is just 4. So I'm going to let you go ahead and do that in your work as well. But then really what I want is I want to have something for that absolute value of x minus 2, because that's going to be, remember what we had before was 0 is less than the absolute value of x minus 2 is less than delta, and I need to find that delta. Well, to find that delta, I can use the conclusion here, and I can divide both sides by 4, and so this would imply that the absolute value of x minus 2 is less than 0.01 divided by 4 would be 0.0025. And so we use the conclusion to come up with that. And so now what can I do? Now I can set delta for that epsilon of 0.01. I can set delta equal to 0.0025. And if I do that, then that's going to guarantee that everything stays in the window. In the corridor from the delta window around x equals 2 to the epsilon window around L equals 3 for the limit. So I'm going to draw a picture of that now, but we came up, does any questions, you can throw it in the chat if you want, any questions on how we came up with that delta for the given epsilon? Once again, this is specifically for section 1.4, which in my world is a lot easier to go back and do after we do it in general in 1.5 for any epsilon, but this is what they're doing. So I'm going to show you a picture, once again, of this function. So remember we had f of x equals 4x minus 5. Okay, 4x minus 5, if you plug it into, if you plug in 0, you get -5 for the y-intercept, right? I'll let you figure out what the x-intercept is, but when you plug in 2, we're up at 3. So if I plug in 1, what are we at? We're at -1. So it's not quite there. But when we're at 2, we actually, when x equals 2, we actually hit the height of 3. So the reality is 3 is my limit that I approach, the height that my function approaches. Let me go back and just right over here. So f of x equals 4x minus 5. Limit, that's the limit. Now we haven't proved it because we only did it for one epsilon. And then 2 is my a. So x equals or x approaches a. Now, once again, if I approach from the right and from the left, what happens here is I have a corridor. So I said let epsilon equal 0.01, right? Well, that means that my window, my epsilon window, goes from 2.99 on the bottom side to 3.01. Now, obviously, my graph is not very accurate because it's not drawn to scale, because I have a tiny epsilon window, don't I? And if I bring that epsilon window over and map it back here, then what I could actually do is come up the way we did with delta. So we found that delta equals 0.0025. And by doing that, we know that every x value in here would map in that corridor. Okay, so that epsilon window that we were given, we came up with a delta window around A. And so this goes to the right, it goes over to 2.0025. And left of that, I'm not very good at math, but 1.9975. Is that right, guys? People? So this is my delta window around A, x equals A, and this is my epsilon window. I'll change colors. This is my epsilon window around what's going to end up being the height, the limit. Okay. Now, doing it for this one doesn't prove that 3 is the limit. We know it's going to be 3 because we can do some other stuff to prove that in general in section 1.5, but this is for a particular value. But somebody else may come along and let's use gray. Somebody, well, that doesn't look very good. Let me just go with green. We'll go green. And somebody says, hey, that's great, you did it for that, but what if epsilon equals 0.001? Can you do it for that? Well, yeah. So we have a smaller window around 3. That'll lead to a smaller window around x equals 2. And this process that I just showed you really is trying to find this is the biggest delta that will work. So this is the biggest delta that works in this case. So once again, what's a number that's smaller than this? Well, 0.0001 would work because I'd be in here even tighter and I'd still be in that corridor, right? So anything smaller than 0.0025 works for when epsilon equals 0.01 as well. Hopefully that makes sense. All right, so I'll give you a moment if you have a chat question. Otherwise, I'm going to go back and we're going to do this in general now, and I'm going to prove to you that the limit as x approaches 2 of that function exists and equals 3. So we're going to prove the limit as x approaches 2 of 4x minus 5 exists and equals 3 by the epsilon delta definition. Okay, so epsilon delta, that's a definition. That was, I gave you the page number in the blue book. But anyway, that was the epsilon delta definition. We're going to prove it. Okay, so first of all, the definition says let f be defined on some open interval containing a except possibly a itself. Well, what do we know? The domain of f is all real numbers, so certainly it contains, it's defined around x equals 2. In fact, it's defined at x equals 2. So we have that, but we have to note it because that's a requirement. Obviously, it's a function because it's a linear function, right? So the only lines that aren't functions are vertical lines. Anyway, so then we need some scratch work. So we need scratch work. let epsilon be any number greater than 0. So this is section 1.5 stuff that I'm doing right now. But we're going to let epsilon be greater than 0. And what I need to do now is I need to find my delta greater than 0 such that, so that's the backwards curvy E. Find that delta greater than 0 such that what? 0 is less than the absolute value of x minus a is 2, right? Is less than delta would imply or guarantee that the absolute value of f of x, which is 4x minus 5, minus L, which is the limit I approach is 3, would be less than that epsilon, no matter how tiny. So I'm picking any epsilon greater, or any tiny number greater than 0. So somebody might pick 0.01, somebody else might pick 0.001. I'm going to be able to use this method to determine the delta that would work. Okay. So by doing this, what I'm going to do, I'm going to continue on the right. I'm going to combine like terms just like I did before. This says that 4x minus 8, the absolute value of that is less than epsilon, which implies that 4 times the absolute value of x minus 2 is less than epsilon. So then what does that imply? This implies that if I divide both sides by 4, by the way, you got to be careful because if that was a negative number, this is an inequality, but the inequality holds because I'm dividing by a positive number. So don't forget that that's not an equal sign. It's a less than sign in case you ever, for some reason, divide by a negative number. All right, but anyway, we probably won't be here. But anyway, what do we have? Over here on the right, we have, we need to find that delta such that 0 is less than the absolute value of x minus 2 is less than delta. So what can I do here? What do you think I can set delta equal to? Epsilon divided by 4. So we're going to set delta equal to epsilon over 4, and then that's going to make everything work. So this is our scratch work to come up with it. And then what we need to do is just put it together and then prove it. So any questions on that before I go back and do this as a proof? Nope, crickets. You guys are all mesmerized. I know what you're thinking right now. You're like, really? You picked this stuff to be gone? But hey, the good news is I recorded it. So after you read stuff in the book, if you think back to some of the things that I was saying or looking at, you're like, oh, wait, what was he saying here? You can look it up. It's on Blackboard. It should be under recorded sessions if you look inside of Blackboard Collaborate. All right, but anyway, so let me erase this then. Now let's go ahead and prove this formally. Okay, so proof. Domain, first of all, the domain of f is all real numbers, so we have that. And then what we're going to do is we're going to do a thing called let. All right, this should have been another color. It's not part of the proof. But this is what we're going to do now on the proof. It's let set. So we already showed the domain. There's some open interval. The real numbers is an open interval, right? From not including negative infinity to not including infinity. So really, this is my open interval containing x equals 2, right? It's a big one, but obviously we don't need that much space for an open interval, but obviously the real numbers is the biggest open interval we can have, so that's fine. Anyway, so we're going to do let set. So the proof, let epsilon be greater than 0. So epsilon is some tiny number that's going to create a vertical window around my limit L, which happens to be a height of 3. So let epsilon be greater than 0, and then we're going to set delta equal to whatever we came up with in our scratch work. And so in this case, it's epsilon over 4. So we're going to set delta equal to epsilon over 4. And then what we're going to do, I'm going to put notes here in purple, we're going to work backwards on our previous screen. So we're going to work backwards from our scratch work, okay? So basically, So this implies, then what we need is, whoops, get back to black. Then 0 is less than the absolute value of x minus a, which is 2, is less than delta, implies what? Well, reality is the left side here, I'm gonna use a different color. What does this say? Since x minus 2 is an absolute value, absolute values are greater than or equal to 0. So the only thing that this orange circle says is that it doesn't equal 0. The rest being positive is obvious, but that just means that x doesn't equal 2. So for limit, remember, we can get as close to 2 as we want without touching it. So this orange part just says that x doesn't equal 2. Once again, that's not needed for you to show it every time. I'm just telling you that's the right side. But the reality is we can use our scratch work on the left side, or on the right side, sorry, and we can just go from here. So this implies, since that we have that chain link inequality, this implies the absolute value of x minus 2 is less than, now we know we set delta equal to epsilon over 4, so we're just going to put that in right here. So instead of delta, we have epsilon over 4. Okay, does everybody see what I did? I just replaced delta with epsilon over 4, and now I can do my work backwards. So then what did we do? Or, let's get that 4 back over. This implies the absolute, or excuse me, 4 times the absolute value of x minus 2 is less than epsilon. And this implies the absolute value of 4 times the quantity x minus 2 is less than epsilon, which implies, I'd be going down the screen, but I'm running out of room here. So this implies the absolute value of 4x minus 8 is less than epsilon, and this implies that the absolute value of 4x minus 5 and then minus 3 is less than epsilon. And this is, going back to notes, this is f of x here. This is my L, right? So basically, what I did is I just proved it because I showed it was defined on an open interval containing A except possibly A itself. Let epsilon be greater than 0. We found delta equal to epsilon over 4, and then 0 is the absolute value of x minus A. So remember, 2 is your A, is less than delta, guarantees that the absolute value of f of x minus L is less than epsilon. So the other thing I should have put in that chart is therefore. So 3 dots means therefore. You can write out the words if you want. We can talk about that again tomorrow. But therefore, we can say the limit as x approaches 2 of 4x minus 5 exists and equals 3. So we're done. I'm going to rewrite that last part. So therefore, 3 dots means therefore. I'll put that. But once again, mathematicians don't like writing on words. Therefore, the limit as x approaches 2, once again from both sides, of 4x minus 5 exists and equals 3. So 3 is the height that we approach, so we are done. So this is section 1.5. You'll have to do a proof like this on a quiz and a test. So the biggest thing, you don't have to do it the day I show up on Thursday, but what you have to do the next tomorrow and into Thursday is work through this stuff, try and make sense of it, and so that if there is something that you're getting caught up on, or that's not making sense, that you ask. I am checking my phone, I am checking WhatsApp, so if you have questions before I get back, throw them on there. Okay, start working through some odds. Similar, we're not going to do a bunch of odds in section 1.4, so for anybody that doesn't like doing a whole bunch of odds, just do a few of them in 1.4, like the one you got to turn in. Okay, just do 2 or 3. Make sure you're getting them okay. And then 1.5 is the one that I care more about, because if you can do it for any epsilon, you could certainly do it for a specific epsilon. So if you take what I just did to prove this was a proof. So this is a proven fact now because we proved it using the definition. But we could take what we did there for that proof, and instead of any epsilon, we could throw in epsilon equals 0.01, and the delta of being epsilon divided by 4 would be 0.0025. So basically what I did before this one, for the same problem, we could do now just plugging in a specific. All right. So let me check the time, 1:56. And get that off the screen. Any questions? I mean, you can beep and chime in if somebody wants to talk, or you can chat. All I see is Carter. Somebody has to talk, so I don't have to stare at Carter. I wasn't staring at you, Carter. You were just in the lower, but now it's you. Are you sure Kylie came back? Kylie, you better say something. Can you guys hear me?
Yeah, we all got you.
All right. Sounds good. What else do you need to know today? Want to see one more? I could probably get it. How many minutes we got? 4 minutes?
Yeah, 4.
Or I could actually, what I'm going to do is I'm going to show you something. I'll show you some concept stuff because that was pretty heavy. I'll do another one in class together on Thursday. So your evens are not formally due, but I do want you working odds in 0.4 and 1.5, similar to what you're going to do. With that, Isaac? Nothing? All right. That's my 3-minute warning. Let me just show you something real quick on the whiteboard. You guys can mute yourselves again. Where'd my whiteboard go? Oh, there it is. Okay. I do want to show you an example because we're going to get into section 1.6 and 1.7, look at right and left-handed limits. So we're just going to look at a split function, and we're going to let f of x equal square root of x plus 1 if x is greater than 0. It's going to equal 0 if x equals 0, and it's going to equal, we might as well just stay with the same one, 4x minus 5 if x is less than 0. And I'm just going to draw this out. I'm going to use color since I got all these pretty colors. We'll let the first one, the square root of x plus 1 is an upshift of the square root graph, right? So that's an arc, not an arc, but like it's half a parabola turned on its side, but it's a curve, right? So that's the square root graph with an upshift 1, right? By the way, I just screwed that up because this has to be an open dot. This is open, right? Because it said strictly greater than 0. So then at x equals 0, that's the closed dot. Okay, so that's a closed dot. The purple one needed to be open. And then I'm going to use red here for this last one. But anyway, this, if you plug in 0, you get to 5. I don't actually hit it, but it's a line with a slope of -4. So we have this, and then we could ask some questions. We could say, what's the right-handed limit? So instead of writing that out, I'm just going to put RHL, the right-handed limit as x approaches 0. So x approaches 0 from the right. So we're going to write the limit as x approaches 0 from the right of f of x. That would be the purple one, right? So that would be the square root of x plus 1. And as I approach x from 0 from the right, I'm going down on a height of 1, right? So the right-handed limit for this function f of x is 1 at x equals 0. And then the left-handed limit, so if I look at the left-handed limit, that'd be the limit as x approaches 0 from the left of this function f of x, but instead of writing f of x, it's actually this one that I would be on. It'd be 4x minus 5. And it comes in and it approaches that height, which is the y-intercept, which is actually 0. Excuse me, no, it's not. It's negative 5. If you plug in 0, you would get negative 5. Now, it doesn't actually hit that open red dot, but it approaches it, right? So that's the limit. So negative 5 would be the left-handed limit. So then what could I say? I could say that the, by the way, also f of 0 is 0, but 0 isn't a limit of anything, right? Anyway, so what I can say is the limit as x approaches 0 from both sides of f of x does not exist. So DN is shorthand for does not exist. So the limit as x approaches 0, remember this is both sides. And the only way a limit is going to exist is if when you approach from the right, it has to be the same height that you approach as you approach from the left. So in this case, I have a right-handed limit coming into x equals 0, and I have a left-handed limit coming into x equals 0. But since they are not equal, these are not equal, then we say that this function does not have a limit at x equals 0. Does that make sense? And I can't hear your bell, so if you got to go, go. Yeah, we're done. All right, thanks, guys. See you Thursday. No, Thursday, no class. That's all right, I'll text you.